Hello, I'm Chang-hoon Lee from Gyeongsang National University in South Korea. It's my great pleasure to get a chance to talk about my work about uncovering hidden dependency in weighted networks via information entropy at the Networks 2021. The paper is available on arXiv, so you can look it up for all of the details. I have to thank my precious collaborators who actually did all the heavy lifting. The motivation to study this problem actually went back to more than 20 years now when I was in high school. There was a theft case in our dormitory and a teacher said, "You may think you are just borrowing your friend's stuff without bothering to tell him. However, if you think he's your friend but he doesn't think you are his friend, you are a thief." So it's a kind of interesting way to express the situation. So I actually suggest you to think about this problem yourself. Is it possible to have a unidirectional friendship relation? And 20 years has passed and we actually know that there is a directional friendship, especially in online world where we are virtually living from last year. For example, on Twitter, you have this following relation, not just a bidirectional friendship relation. So this is my Twitter account and my dear friend and colleague, Professor Young-ho in University of Seoul. I follow him and he followed me back as a mutual friends. And of course, I follow the journal Nature, but in contrast to this mutual case, there is no reason this journal Nature follow me back, just the ordinary researcher. So this following relation explicitly implies the directionality. In contrast, you may think that Facebook is different from Twitter because usually you have friends to each other on Facebook, but it's not always true in fact. In reality, you are supposed to like your boss post on Facebook because of this kind of a social pressure. So maybe it's just the difference between explicit direction and implicit direction. So our main question is there any way to extract this implicit dependency between the two nodes in seemingly very bilateral relationship in a network? So I took the example, we have two nodes here, both are denoted by index I here, and for the record, the number of neighbor or degree is the same for both cases. Both the left hand side and right hand side has 4 neighbors, and even the strengths, the sum of all the weight around the node are also the same. So in this case, if you only characterize this particular node with the degree and strengths, you will get the same values. But of course, almost intuitively, you know that it's very different, or the nodes are situated in a very different circumstance. So clearly there is something different. Of course, this weight is quite homogeneous. If you look at the right hand side, the distribution is very heterogeneous. So weight distribution is different. So of course, when we talk about the distribution, we have to normalize these numbers. If you divide each of these weight by these strengths, you will get this probability-like value called normalized weight. We denote this normalized weight by this tilde symbol here. If you think about this weight, for example, as a duration of phone call you make with all of your friends, this probability show the fraction of time you spend with the particular neighbor of yours. So in this case, the node I distribute the phone call duration time more or less equally to all of the neighbors. But in this case, you spend most of your time talking to J or M. So we already see some asymmetry between the seemingly bilateral relationship here. Mathematically, it means that the Wij tilde and Wji tilde will be different. Even if we start from the undirected weight, Wij, because of the difference in this strength. So because of this, the normalized weight is intrinsically asymmetric because sometimes sadly, the importance of node J for node I and the importance of node I for node J are different in general. So to examine the asymmetry here, the first thing you can do is obviously you can just measure this simple correlation between this and this for a network. So to test that, we use 2 types of different data sets. The first one is the World Trade Web data between the nations, spanning like 50 years. So in this series of networks, for each year, the networks representing the trade volume between the nations. So that is the first data set. And second data set is quite different one, which is Annals of Joseon Dynasty. And in this network, the weighted network represents the edges between the people described in this historic document. The weights are defined as the number of sentences mentioning people pairwise together. So there are very different types of networks. So we will actually see the clear difference. So as I already mentioned, the first thing you can try is Pearson correlation between the normalized weight Wij tilde and the Wji tilde in both directions. So we call this mutuality. So large value of mutuality means that these two directions are more or less similar. And if the mutuality value is very small, that means that the relationship itself is quite asymmetry in terms of this relative importance. And both of the network I mentioned are timestamps. So we can actually track the temporal changes of this type of mutuality. So if you look at this, the first one, the World Trade Web, shows this pattern. If you look at this, compared to this degree correlation or the associativity shows drastically different behavior, especially on this 80s and 90s, potentially because of this, the collapse of the communism or the oil shock. But if you look at the mutuality value, they do not change that much. That means that the mutual relationship between two nations are relatively stable compared to these drastic structural changes over the course of these very large external changes. And of course, we need to compare this value to null model. So by null model, we mean we shuffle all of the weights for a given network structure. So the structure is the same, but the intrinsic correlation between weights will be completely destroyed. So if you look at the World Trade Web case, if you shuffle all of the weights, the mutuality is actually much larger than the reality. That means that the international relationships are intrinsically very asymmetric. When it comes to the trading relation, usually there is a big country economically and small country. Because of this severe heterogeneity in economic scale, usually the relationship is not that symmetric. And in contrast, in terms of the relationship between people in historical record, it shows the very similar mutuality, even if you shuffle all of the weight. So relationship between people in this historical document are much more mutual. So the next question or the next step is how to quantify this intrinsic directionality from this weight distribution. So our idea is to use the concept of information theory. If you go back to this example, as I already mentioned, this normalized weight has become the probability variable. In information theory, there is a very relevant concept in statistical physics, which is Shannon's information entropy. So you can just measure this entropy value. And of course, this entropy measure represents the homogeneity of a weight around node I. This entropy measure has this scaling property. If most of its weights will be similar or uniform to each other, they will scale like log of the original degree. And if a single weight or a few weights dominate this local region, the entropy goes to zero. So because of this scaling property, if we exponentiate this entropy measure, we will get this very nice property. So for almost uniform weights, this so-called effective out degree is reduced to this original degree in the case of the almost uniform weight around each node. For a single or a few weights are dominant, it will goes to one or very small value. So as you can already see from our naming scheme, this effective out degree is the effective number of important neighbor. So if you actually calculate the reference side, as we can expect, the value is very close to 4, covering all of the neighbor. And as we expect, this effective out degree is close to 2. And in practice, we can just taking up to the top k tilde neighbors in terms of weight. The important part is this, from node I. If we repeat this same exact process for all of node, we will have this sort of intrinsically directed backbone of this entire network structure. It's the emergence of a hidden directionality or hidden dependency from the originally undirected weight network. So to quantify the properties of this extracted directed backbone, we can come up with some characteristic measure like a relative edge density represent how much of the original interaction is recovered, and the reciprocity, how reciprocal each of the directed edges. We apply this directed backbone extraction process for the World Trade Web and the Annals of Joseon Dynasty data. The conclusion is very consistent with the result from the mutuality value I mentioned before. For instance, in the case of World Trade Web, fraction of reciprocal edge is very smaller than the shuffled weight case. So it's very consistent with the mutuality result, because if we shuffle the weight, we got this larger mutuality than the reality. And also in terms of reciprocity, the randomized version shows the larger reciprocity. Again, this confirms our expectation, which is the international relationship is quite asymmetry. And if you just construct the directed backbone, you will naturally get this effective incoming degree as well. This effective out degree means the number of nations you consider as important neighbor. But this effective incoming degree means number of countries who think you are an important trading partner. So in some ways, this effective incoming degree represents the importance of your existence more in this whole trading relation. So if you look at the China and US case, you will see the very large development of China over the past 50 years. And we check the 4 representative cases here. So here the local reciprocity is a local version of the reciprocity. Number of neighbors you think as important and they also think you are important, divided by this effective outgoing degree, the number of country you consider as important. And the attraction ratio represents the ratio between the countries who think you are important and the countries you think as important. You can see some interesting cases here. China, US, Canada, and India. They all have a very different trajectory over the past 50 years of the history. And finally, we would like to give you some supplementary analysis. The first one is comparing our result with this so-called multi-scale backbone method developed by Serrano and her colleagues. This method has some similarity and a big difference from our method. Their biggest difference is that in the limiting case of all the edges are mostly uniform, our method treat all of those edges are equally important. In contrast to this multi-scale backbone method where they treat all the edges are equally trivial, because in that method they try to pinpoint the most statistically significant edges among the local weight distributions. In that way, their criterion of selecting these backbones is quite different from ours. The original multi-scale backbone method didn't use this directional information, so we adopt the direct version or direct variant of the multi-scale backbone method to compare our result. And of course, we have to compare our result with this most purely topological structure composed of this power law degree distribution and the weight distribution. Each of them is characterized by this exponent gamma and the lambda respectively. And we measure many of the quantities we presented with our empirical data, such as the relative edge density and the reciprocity and mutuality and the correlation between these two quantities. So we consider this as some kind of baseline result for the comparison with the empirical data. These two supplementary analyses are included in the 2 appendix sections in the revised archive version. So please go check that paper for all the details here. So in summary, we provide the whole framework to quantify the homogeneity or heterogeneity of weight distribution. And based on the information theory, we provide concept of effective degree to quantify the intrinsically hidden dependency. Thank you for your direct attention. If you have any question or comment, just email me. And finally, stay safe, wear a mask, and get vaccinated.